Yeah, then I can sleep. I was going to say drink, but I'm like, nah, I have kids now. I can't drink. Yeah. He's going to come to the. I think they're going to come to the picnic. There's just one kid. My wife also kind of. Oh no. All right. Okay. So hopefully you're convinced that convex co-compactness in higher rank symmetric spaces is uninteresting, or at least I told you that. So now I want to show you about a different way to study sort of convex compact structures that whose geometry sort of stands in for or represents many different kinds of interesting representations into higher rank Lie groups. And really I'm going to focus on one higher rank Lie group. That's G. That's G. The projective general linear group of a vector space V. So here V is just a vector space, a copy of Rd plus 1, a real vector space. And G is its projective general linear group. So the general linear group, the linear automorphisms, divided out by the diagonal, the multiples of the identity. Okay, so what is X? X is not the Riemannian symmetric space. X is the real projective space, the projectivization of V, which is a copy of RPD. Okay. And so there's no invariant notion of metric or connection in RPD, but there are straight lines. Okay? So there are straight lines. So what is a straight line? Well, it's just the projectivization of a two-dimensional subspace. Okay, so one-dimensional subspaces are points, two-dimensional subspaces are lines, and between any 2 points, there's a unique line. Okay, so we can talk about convexity. So let's assume, let's let M be a PGLV, comma P of V manifold. Okay, definition. M is called convex if any path in M is homotopic to a straight line segment. Okay, so that looks like before. And now I need to add the word unique. So in particular, notice that, I told you that any 2 points are joined by a line in projective space. But that line is a copy of RP1, right? It's a circle topologically. So there's not a unique line segment between any 2 points. So there's a bit of an issue. What I really want here is a straight line, is a path that any path can be homotoped rel m points to a unique straight line segment, not 2 different ones. Okay, so in particular, the real projective space itself is not convex. If you're hoping that would be a simple example to think about, it is not. Okay, great. So so I'm going to call it a proposition this time because it's slightly non-trivial. if M is convex, then the developing map from the universal cover into projective space is again an embedding. And its image, which I'll call C again, is a convex subset of projective space. And again, convex has the same definition as before. Any 2 points, any path in the set is homotopic to a unique straight line segment. OK, so it's nice. It's not a weird. It's not actually a weird notion. It really is equivalent to, yeah. Let me say it this way: equivalent to the fact that C is actually contained in an affine chart of projective space. So the complement of a hyperplane, D. This is an affine chart. So it looks just like a copy of affine RD, the affine space. And it's convex there in the usual sense. OK? So the universal cover embeds in projective space. And if you look in a nice affine chart, the image is completely contained there, and it looks just like a convex set in RD. OK. I want to restrict to a slightly more specific class, that of properly convex manifolds. So I'll call M properly convex if C is properly convex, meaning in this affine chart, it's also bounded, or for a choice of affine chart. The convex set that you see is actually bounded. OK. So let's see. All right. So let me talk for a moment about closed manifolds. Well, actually, I'll talk for a little while about closed manifolds. So let's assume M is closed. Oh, you know, I guess I wanted to call this omega now. But anyway, OK. Assume M is closed. Then let me call C omega now. I'm sorry. So omega, the image of the developing map, is a properly convex set. It's open. OK. And the holonomy representation, let me call the image of the holonomy representation. Let me call that gamma. That's a discrete subgroup of PGLV. Sorry, open, properly convex. So gamma is a discrete subgroup, and it acts on omega freely, properly discontinuously, and co-compactly. OK? And historically, the name for this is, we say omega gamma divides omega. And we say omega is a divisible convex set. So if you want to learn more about these things, you should type that into Google, not convex, PGLV, P of V structure. OK. So let's look at a few examples. OK, so here's an easy properly convex set in the projective plane. It's a triangle. OK, so I could take the positive span of the standard basis. That's a cone in R3. I can projectivize it down to RP2. OK, so this is in RP2. OK, and the projective general linear transformations that preserve this triangle are exactly the positive diagonal matrices. Well, plus the symmetric group, which exchanges the vertices. Okay, but ignore that. Okay, so I can take gamma. I'm going to take gamma to be the matrices with powers of 2, with any power of 2 along the diagonal. So this actually acts. This actually divides omega, and it's kind of nice. You can see this. So okay, it divides omega. It's yes. Okay, it's isomorphic to z cross z. It divides omega. The quotient is a torus. So a properly convex projective torus. Okay. And if you want to see a picture of the universal cover of the torus, which we normally draw as a grid in R2 in this triangle, you can actually do that by taking your favorite sort of transverse one-parameter subgroups here, which align with this lattice. And it looks something like this. Okay, so that's not the world's best picture of this, but so you can really see the usual grid for the torus right there. Okay. The next example, those lines are, if I take the exponential of 1, 0, minus 1, and the exponential of 0, 1, minus 1, and I act on some base point. These are one-parameter subgroups. I move the base point. Here's a base point. I move the base point around with that one-parameter subgroup. That's this one. I do the other one. And then I move that around with the lattice. That's what those lines are. They're sort of a natural coordinate system for, yeah.
You can do it for straight lines, right?
Not maybe for this one. Yeah, you could do it for straight lines with this one. But OK, that's less exciting, I think. Yeah, there are other properly convex projective structures on the torus for which there is no straight line coordinate system. OK. So, OK, the next example is hyperbolic manifolds. So POD1, comma HD, the hyperbolic geometry that we just talked about in depth, actually embeds as a subgeometry of real projective geometry in the following way. You take a quadratic form of signature D1 on V. You look at its negative lines. That gives you a cone in V, a symmetric round cone, convex cone. Its projection to projective space looks like a round ellipse. And the projective automorphisms, the automorphisms that preserve this round ellipsoid, is precisely the orthogonal group of that quadratic form. So any closed hyperbolic manifold gives you a group dividing an ellipsoid in projective space. Okay, so if gamma is a lattice, a uniform lattice in POD1, then gamma, this feels like an empty statement. So gamma, thought of as a group of matrices in the projective general linear group, divides HD, thought of as a properly convex set in projective space. OK? And then, so that's great, but so far nobody looks excited. There are many other interesting convex divisible sets. And one way to get them is by deformation. So there's a holonomy principle for convex for properly convex projective manifolds. due to Kozul. It says if you deform the holonomy representation, well, let me just say it this way. If you deform a discrete subgroup of PGLV that divides omega, you can deform omega a little bit, and your deformed group will divide the deformed convex set. OK, so I can take Teichmuller space, a space of hyperbolic structures on a surface of genus G. We know from lecture 2 that this identifies with a component of the representation space of the fundamental group of a surface into the isometries of H2, which I'll write now as POD1. And I can deform. Point is, this lives in a much bigger representation space. The representations of the surface group into PGL, V is R3 now. OK, that's a much bigger representation space. And so we get a deformation space. Let me just write it this way. Of convex projective structures on surfaces which come from deforming hyperbolic structures. And in fact, Benoit proved that not only is there a local holonomy principle, but actually there's a global statement. You can take limits of the holonomy representations and again get holonomy representations. So this is actually equal to a component of this representation space, which is called the Hidgen component for PGL3. OK, and this is actually much bigger than this, and it's easy to see that, for example, by a bending construction. You can sort of bend hyperbolic structures into projective space in a non-trivial way. OK, so there's a huge number of interesting convex projective surfaces of genus G, greater than or equal to 2. And in higher dimensions, there's interesting constructions as well, but I'm going to, for the sake of time, not cover that. OK. Questions about those examples? OK. All right. So I want to tell you now a nice theorem that looks a lot like the theorem we talked about last hour. But it's about convex projective manifolds. OK. Sorry, what? Oh, yeah. So yeah, I should say that a very detailed study of this deformation space of convex projective surfaces goes back to Choi and Goldman, where they parameterized the space using sort of modified Fenchel-Nielsen coordinates, and they showed this closeness as well. I guess Benoit showed it for more general limits of convex projective structures. Yes, so I should.
And in all dimensions.
What's that?
And in all dimensions.
And in all dimensions, yeah. So I should say Choi Goldman. Thank you. Is this setting? Yeah, that's a very beautiful theory. If you don't know about convex projective structures on surfaces, that's a really great thing to learn about. It's very beautiful, and everything works really nicely. And there's still lots of interesting questions about them. OK. All right. Theorem. This is due to Benoit. OK. Suppose that gamma divides a properly convex set omega. Let me suppress those words.
Does it also work for convex surfaces, or it's only for closed surfaces?
Good question. So if you take the deformation space of convex co-compact surfaces, hyperbolic surfaces, you can deform them a little bit. Well, OK, that's more complicated. I'm going to say stuff about that later. Let me not try to answer that right now. The answer is yes, in some sense. Yeah. OK. All right. So suppose gamma divides omega. Then the following are equivalent. And let me get the order of these things right. OK. 1. So this is slightly different than the order I used before. I'm sorry, but there's a reason. OK, gamma is hyperbolic. And let me say there exists a boundary map from the Gromov boundary of the group to the boundary of omega, where the boundary of omega here, I literally just mean the boundary of omega as a subset of projective space. OK, I literally just mean this circle. OK. OK, and this is a continuous equivariant embedding. 2, the boundary of omega is strictly convex. OK. And that means here's omega, here's its boundary. That means if I take any 2 points in the boundary, the interval connecting them, the projective line segment connecting them, lies inside omega, inside of the interior of omega, for any 2 unequal points on the boundary. OK? So in other words, there's no flat pieces in the boundary of omega. There's no line segments contained in the boundary of omega. OK, I'm going to focus on these, but let me just add a third one in blue. The boundary of omega is C1. OK, what does C1 mean? Well, everybody knows what C1 means, but in this context, let me just say how I want to use it. That means that at each point of the boundary, there's a unique supporting hyperplane, a unique tangent plane. OK, so this is not true, for example, of the triangle. The triangle is not strictly convex even. OK. So it turns out that these are all equivalent. And the equivalence of strict convexity and C1 comes from a duality idea that I don't have time to explain. But let me just say, not only do I get, because of this equivalence, if any of these conditions are satisfied, then omega is strictly convex in C1. So I actually get another boundary map, which I'll call C star. And it maps, now I realize I haven't left nearly enough room to say this. OK. OK, and it maps the boundary of the group to the boundary of the dual convex, which don't worry too much about what that is. It's just the supporting hyperplanes. So it's a subset of the dual projective space, the space of hyperplanes in P of V. What is it? Of course, we take the boundary map. It gives us a point. We take the unique supporting hyperplane there. OK? So just as in Andres' lecture, not only do we get a boundary map with image and projective space, we also get a boundary map with image in hyperplanes, and what he called D-1 planes. Yeah, and your NASA. OK, let's write that too. Put this in parentheses. Well, OK. All right. All of these imply that the inclusion of gamma is a NASA. OK. Yeah, that's right. Yeah, so in particular, these two boundary maps are a NASA boundary maps for the representation. OK. Let me say very quickly some ideas. Again, I don't want to think about 3 right now. You, in the problem session, will prove this theorem, at least the equivalence of 1 and 2. Or you will have the option to prove this theorem. Don't have to. Don't want to be forceful. You don't have to do it. There's actually way too many problems, so you might not get to this one. But let me illustrate with a couple of pictures the proof. OK, how do we prove 2 implies 1? OK, so I've got omega. It has strictly convex boundary. And I want to prove that gamma is hyperbolic. Oh, actually, I need to introduce the Hilbert metric. I'm sorry. OK. All right, there's a crucial tool here that I somehow forgot to introduce called the Hilbert metric. So there's no invariant metric in projective space. However, if you restrict to automorphisms of a properly convex set, there is a nice metric. It's the Hilbert metric. So what is it? If I take 2 points in omega, and I draw the straight line between them, that intersects the boundary of omega in 2 more points, A and B. And I define the Hilbert metric, the distance between x and y, to be 1/2 log of the cross ratio. So this is the cross ratio. So remember, these are 4 points on a copy of RP1. So you can just calculate the cross ratio in your favorite way, in R essentially. OK. And in fact, this is a metric. It makes omega a proper metric space. It's complete metric. And so it follows that any discrete group, gamma, which preserves omega, actually acts properly discontinuously on omega. So the search for properly convex projective manifolds, closed manifolds, boils down to simply finding properly convex sets and discrete subgroups which preserve those properly convex sets and act co-compactly. You don't need to worry about proper discontinuity. OK. So that's great. Questions about that? I think a lot of you have seen that before. OK. All right, so how do we, let's sketch the proof of 2 implies 1. Right? We're going to 1, right? OK, so I've got this strictly convex set, omega. OK. And I want to show, OK, I want to use the Schwarz-Milner lemma to show that gamma is hyperbolic. Since it's acting co-compactly and it's on this metric space, all I need to do is show that the metric space is hyperbolic, is delta hyperbolic. OK, so how do I check if something is delta hyperbolic? Well, I draw a triangle, and I ask, for a delta such that the delta neighborhoods of 2 edges contains the third edge. OK? So lemma, for any triangle, there exists such a delta. Right? That's pretty easy. OK. So for T triangle, there exists a delta, but it depends on T, obviously. OK, but the point is, because the boundary is strictly convex, I can actually consider triangles with points on the boundary of omega, ideal triangles or partially ideal triangles. OK, and in fact, it's a lemma that if you look at 2 edges going into the same ideal point, the same point in the boundary of omega, those edges actually stay bounded distance apart in the Hilbert metric. So in fact, this is true for partially ideal triangles and even fully ideal triangles. OK, well, then you just need to show that the space of all triangles, including those which contain vertices in infinity, is actually co-compact under the action of gamma, using the co-compactness on omega. And you can just take the max of all of those deltas. Okay. Okay. All right, what about the converse implication? Let's not talk about that. So Sam raised a good point, but let's talk about it. The Hilbert metric is a geodesic metric space. The geodesics, as you might guess, are straight line segments, but there actually can be more geodesics in some cases. But in fact, that doesn't happen when the boundary is strictly convex. But if you, so yeah, that's a technicality that's important to know about, but let's ignore it right now. It's actually kind of annoying sometimes. OK, so let's prove not, did I erase the theorem? No, OK, let's prove not 2 implies not 1. OK, so if not 2, then the boundary of omega fails to be strictly convex. So there's a segment in the boundary. And now I think you can see what the problem might be. If I try to do the same argument, I take the limit of compact triangles, it might end up being a triangle whose third edge is entirely in the boundary. So if in fact, that really is a deal breaker here. If I look at a triangle whose third edge is this maximal segment in the boundary, you can calculate that if I start taking line segments like this, by a simple cross ratio argument, sorry, why did I want to do this? Yeah. Yeah. So right. Well, the point is that AN and XN are both converging to A, say, and BN and YN are both converging to B. Yeah. So yeah. So if I start to take triangles that look like this, yeah, let me not try to say this because I'm going to confuse myself. But you'll see that those cannot satisfy delta thinness for any delta. Yeah. I mean, essentially most points of this edge are getting infinitely far away from both of these edges, and these edges are also getting infinitely far apart as well. So it's just a calculation. But you can sort of see why this triangle is not very thin looking. OK. OK, great. All right, so I want to go now to, in the last 13 minutes, I want to go now to convex projective structures with boundary. So I want to try to generalize this Benoit's theorem to look more like the theorem we talked about last hour, which allowed a wide class of representations because there's lots of different hyperbolic compact convex hyperbolic structures with boundary. Divisible convex sets or convex projective structures on closed manifolds are great, and there's a lot of cool examples, but they're still fairly rare in high dimensions. So this theory will allow us to look at a lot larger subset of the representation space. OK. So all right. So now I want to. OK. I want it to be. I want M for the remainder to be properly convex, compact, with non-trivial boundary. And again, remember what this means. It means that I've got a projective structure on the interior of M, but I can actually enlarge that past the boundary. So here's M. So here in this picture, M is an annulus with a closed annulus. And I want it to be included. I want to know that it's included in a larger thickening. Which is also properly convex. OK. So what's the picture? So let's take, and this is an open manifold. The developing image for M prime, let's call that omega. And the developing image for M, let's call that C now. C is a closed convex subset of omega. It's closed in omega. It's not closed in projective space. So the basic picture is this. Here's what omega might look like. C might look like this. OK, so I need to choose a color here. Choose red. Red and blue. OK, so here's C. OK? And the action, the fundamental group of the annulus is Z. The action is sort of doing this. OK. All right, and I label these for a reason. So C is a closed subset of omega. So its boundary in omega, I'm going to label boundary n for non-ideal boundary. And that's just a lift of the boundary of M. So in this case, that's a lift of these two curves. The lift of one is here, and the lift of the other is here. But also, C, if you take its closure in projective space, you get more points. You get sort of limit points, points at infinity. And I'm going to call those the ideal boundary of C. OK, so those are just the points in the closure of C intersected with the boundary of omega. OK. Great. Let's see, can I fit the next thing over here? OK, so all right. So now, the reason I wanted this thickening is I can use the Hilbert metric on omega to make a metric on C, right? So C, so let me write it this way. So gamma, which is the holonomy image for M, gamma acts on C properly and co-compactly, like a covering space action. And it acts by isometries of the Hilbert metric on omega. OK? So let's apply lemma 1, or fact 1, the Schwarz-Milner lemma. That tells me, well, I guess maybe I want to, let's assume gamma is hyperbolic. OK, sorry. I'm going to assume gamma is, well, OK. Sorry, let's not assume that yet. So fact 1 implies that the orbit map from gamma into C is a quasi-isometry. OK? And, well, OK, let's just go to the hyperbolic case right now. Erase this. OK. All right, so let's assume gamma is hyperbolic. OK, so fact 2 tells us that the orbit map extends to an embedding of the ideal Gromov boundary of gamma to the visual boundary of the metric space C together with the Hilbert metric d omega. This is continuous equivariant embedding. OK. So that's great. That looks like Benoit's theorem, right? We've got a nice co-compact action on some subset of omega. And we've got a boundary embedding into the visual boundary of C. But the issue here is I don't know whether or not this equals the ideal boundary of C. So I really want a boundary embedding into projective space. But this is just an abstract visual boundary of a metric space. So what could go wrong? Well, if omega has segments, if it's not strictly convex, OK, maybe C looks like this. That was blue. OK, and we have a whole segment of red here, a whole segment of ideal boundary. So an easy calculation for you to do is if I take two lines with distinct endpoints in this segment, these actually are a bounded distance apart. So these lines are at bounded distance in the Hilbert metric. So they really are the same point in the visual boundary, but they're going towards different points in the ideal boundary. So we don't get, if there are segments, we don't actually get any map into projective space. And we don't like that. We want to work with subsets of projective space. So the solution, which I think is pretty cool, and this is a small piece of recent work of myself with Francois Guérateau and Fanny Castle, is the following. So again, assuming gamma is hyperbolic, if the boundary of M is strictly convex, so in other words, my projective structure on M is convex and its boundary is strictly convex in the same sense. That's the same thing as saying that the boundary N of C is strictly convex. Then the ideal boundary of C has no segments. So in fact, and we get this boundary embedding that really is a homeomorphism to the ideal boundary of C, a subset of projective space. OK? So if the geometry of the boundary of your actual manifold is strictly convex, something you can just look at in the manifold itself, then when you lift to the universal cover, the nicest possible thing happens. And the sort of Gromov boundary of the group is naturally just the limit points of your universal cover in projective space. OK, so let me just state now, this is, like I said, a piece of a larger theory. Let me just state now a theorem. OK. It's due to myself with Francois Guérateau and Fanny Castle. I should say Fanny is going to talk about this on Monday if you're still here. And a similar theorem, not quite the same, is due to Zimmer in independent work. OK, so assume that gamma. Let me say it this way. OK, so let gamma be hyperbolic. Rho, a representation of gamma into PG of V. Then the following are equivalent. Now I'll try to make a connection to the old theorem called convex structure prime. Okay, there exists M compact, properly convex PGLV P of V manifold with boundary of M, if it's not empty, strictly convex, such that its fundamental group identifies with gamma, and rho is exactly the holonomy representation. So that's equivalent to, there's really only two conditions, to boundary embedded prime, which says the following, and it might be tough to fit this here. There exists C from the boundary of gamma to P of V, C star from the boundary of gamma to P of V star, which are continuous row equivariant embeddings such that A1, they're transverse. The point in projective space corresponding to eta is in the hyperplane corresponding to eta prime, if and only if eta equals eta prime. A2, the action is dynamics preserving, which means essentially that for gamma in gamma, if we look at the image of the attracting endpoint of gamma in the boundary of the group, this is an attracting fixed point, or the unique attracting fixed point for rho of gamma, and C star of the backwards endpoint of gamma is the repelling hyperplane. OK, for rho of gamma. OK, and these two together, by work of that was already mentioned by Andres, GGKW or KLP, implies that these two actually tell you the representation is a Nosov. OK. And there's one more condition that you need, C, and let me write it this way for brevity. Rho preserves some properly convex set. OK. So in the world of representations that preserve a properly convex set, being a Nosov, having these nice boundary embeddings is equivalent to being the holonomy representation of a properly convex, compact, projective manifold whose boundary is strictly convex. And I'll just say, I think it's very interesting because this allows you, in the same way we talked about for hyperbolic structures, to make all sorts of new examples of Nosov representations by just taking pieces of projective space, convex pieces, and gluing them together in a convex way. And this strategy is evident is what we use and work with Sam Ballas and Gaesan Lee in the context of three manifolds, and also in this same paper where we actually construct right-angled Coxeter groups. We show that virtually all of the Wimberg right-angled Coxeter groups, except the ones on the boundary, are a Nosov. OK, finally, let me just say, I'm sorry. If gamma is not hyperbolic, I have no idea how to characterize the condition of being the condition CS prime here. And I think it would be extremely interesting to come up with some sort of condition mimicking something like this, which characterizes this large class of non-hyperbolic holonomial representations. OK, thanks. Yeah.
I think I'm a bit confused by that proposition down there.
Yep.
Because, so you say if the boundary of M is strictly convex, which the blue part is the width of that,
Yep.
then that's strictly convex.
Yep.
Then the red part has no line segment.
Yes.
So does that not mean that the whole thing then is strictly convex?
Yeah, it does mean that.
But I thought the whole point was to work to get results for properly convex things that are not necessarily strictly convex.
The whole C will turn out to be strictly convex, but omega doesn't have to be strictly convex. Yeah. So the point is, you take a properly convex omega, which isn't strictly convex necessarily, but you have a representation that preserves it, right? By some, it's hard enough to find a strictly convex one. You found a properly convex one, and you want to know whether that representation is a Nosov. Well, you can just sort of look at the convex hull of the limit set, take the quotient, and just examine that properly convex manifold, and just look at its properties. Is it compact, and can you make the boundary? Can you extend the boundary a little bit so that it's strictly convex? If you can, then you know that everything works very nicely, and you have boundary maps and a Nosov representation and whatnot. I will say, too, that I don't actually need that the boundary of M is strictly convex. All I need is that it's just coarsely strictly convex. I don't care if there are segments in it. I just care that there aren't infinite segments in it. So I could have large patches, large compact patches, which are flat in the boundary. That doesn't matter. So in particular, if you can take a piece of projective space that's convex and glue it together in some way that you get a manifold with convex polyhedral boundary that really is strictly convex, like coarsely strictly convex, you've made one of these representations.
So like a triangle.
What's that?
So like a triangle.
A triangle?
Yeah.
No. Well, well, yes. If you glue together, yeah. Well, I don't know. How are you planning to glue together a triangle exactly? Maybe think about maybe gluing together a hexagon. OK, here's a hexagon. And I'm going to glue this side to this side. I'm going to do something really boring. I'm going to make an annulus by gluing this side to this side, using a projective transformation so that when I glue the next copy of this on, it looks like this. And I still have strict convexity. I still have a strict angle there. Then that's going to give you a compact projective manifold whose boundary is coarsely strictly convex. And it will satisfy this theorem. So you can just make tons of these, the same way that you try to make hyperbolic manifolds by gluing together fundamental domains. Other questions? Yeah.
This last condition C, is it the same as asking that the image of psi is included in some effect chart?
No, that's a good question. So you might think if I look at the image of C, and it happens to be contained, if it's not contained in an affine chart, you're screwed, right? But it could be contained in an affine chart. For example, if gamma is a free group, then this is going to be some Cantor set. And Cantor sets pretty much will be contained in some affine chart. They're not big enough to really cross every hyperplane. And you might say, OK, I'm going to take the convex hull of that, and I've got a properly convex set. Well, in fact, you got to be careful, because that thing is not necessarily invariant under the action. Yeah, so it's not. So think about it. What you can phrase this in a way that only talks about these things. And I'm sorry, I will stop after this. OK, if I take 2 points and they're hyperplanes, and I look at the rest of the limit set, the rest of C of gamma. If it's completely contained in this half space, then I can do what you said. Yeah. If the boundary is connected, that's not quite enough. But actually, Zimmer, who I mentioned before, has a condition. Let me say it is enough if your representation lies in POPQ. That's a nicer situation. But Zimmer actually gave conditions, and it's essentially your boundary is connected. It's essentially slightly more than connected. It essentially implies that your group is not an amalgamated, is not a sort of free product of surface groups and free groups or something like that. You need something slightly more than a surface group to guarantee this works every time. But I will say, if you, there always is an embedding of PGLV into a larger PGLV prime, so that the image of this representation preserves some properly convex set. So if you really, if you've got a representation you're really married to, and it doesn't preserve a properly convex set in P of V, you can just go to a bigger P of V prime where it does preserve a properly convex set, and then you can test, what you want to test about it there. Yeah.
Okay, let's thank one more time for and we'll resume at